Hello, my name is Blake Dewey. I'm from Johns Hopkins University, and today I'll be presenting on a disentangled latent space for cross-site MRI harmonization. One of the largest problems that we run into when we talk about medical image analysis with respect to MRI images is the inconsistency in MRI acquisition techniques. MRI is a flexible medical imaging contrast, but this makes it difficult to standardize protocols between sites and vendors. And so far, other harmonization methods have required either traveling subjects or generative adversarial networks, which can be expensive to acquire or difficult to train. For this study, we had 3 different sites involved: IACL, the brain development data set, specifically the Guy's Hospital subset, and 2 internal data sets to Hopkins, which we've labeled Site A and Site B. We have here 2 MRI modalities, the T1 weighted images and the T2 weighted images. Each site has a different acquisition method, which we can especially see in the T1 weighted images in the gray-white contrast, which is strikingly different between the acquisition methods. To perform this kind of work, we're going to have to go back to our MRI contrast theory, specifically that there are underlying tissue parameters, which we can write as a vector of betas, that are affected by a pulse sequence, which we can write as a vector of thetas. We can then think of the MRI as a function of these 2 inputs at each voxel. And hopefully, we would be able to extract these values from an image using an encoder network. But to do this, we would need a disentangled latent space. Specifically, we need an encoder that separates images into theta and beta components. So say we have 2 images. These images are of different contrast, but they share anatomical features, i.e. they're of the same person at the same time. This is commonly done in MRI. We have then feeding them through an encoder network to produce a theta and a probability map. That probability map can be run through the straight-through Gumbel softmax, which is a differentiable operator that allows us to approximate the argmax function and give us a one-hot encoded vector at each of the input image pixel values. We can then introduce randomization to encourage the separation of theta and beta. So after randomization, we get one of the 2 input thetas and a beta tensor that has been selected from each of the input beta tensors, specifically channel-wise. So if we have a beta tensor that has a channel depth of 5, we can actually have 32 possible combinations of beta here. These are then fed into a decoder which synthesizes images from theta and beta to produce approximate images. These images then match up to input images based on the theta value that they are given. We can see here as a 1 or a 2. Before we get into the training method, let's talk about the network design. Specifically, we have a simple UNet, which is reused, or at least the architecture is, between the encoder and the decoder. And we can see the only difference here is on the output value, where it will either go to the encoding heads in the encoder, specifically a theta head, which has large unpadded convolutions to reduce the dimensionality of theta, or the beta head, which uses small padded convolutions to create a beta tensor of a channel depth C beta. On the reconstruction head, we can see that we have small padded convolutions to create our output image. So how do we do this training? Specifically, we'll need 2 inputs: the T1 weighted image and the T2 weighted image from a single subject that was acquired at the same time. As I said, this is commonly done in MRI. We can then feed these images into the encoder to produce 2 different latent spaces. Specifically, the T1 weighted image having a theta value here of negative 1560 and a beta tensor here, which you can see, and the T2 weighted image, which has a theta value of negative 112 in this particular instance, and the beta tensor that is fairly similar to the T1. And the reason that is we are imposing a loss function between these 2 betas, since as they have the same anatomy in the input image, we would want the beta values, which represent anatomy, to be very similar. As I mentioned, we do a randomization where we pick a random theta, and we swap out channels of the beta values randomly between each of these. So we have a random combination of beta channels for each of these 4 options. They're sent into the decoder to produce 4 different synthetic images. We can see that we can match these images using the theta value to our original images. This allows us to calculate a reconstruction loss that we can include in our final loss function. We can then repeat this for multiple images from multiple sites. And the result is a theta spectrum that we can see ranges from T2 weighted images on the far left to the heaviest T1 weighted images on the far right. We can put in our testing images from each site and see where their theta values lie on this spectrum. And we can see that each site creates a separate mode on this spectrum that has a unique distribution. We can extract specific theta values and synthesize an image of those contrasts to show that each of these modalities is represented in this distribution of thetas. Beyond that, we can also see that we can produce images that are not acquired by any MRI imager from any of these sites in this value of -800, which we can see is somewhat of a combination between T1 and T2 weighted images. We can also see that if we put in T1 weighted images from each site, we get relatively similar beta tensors, which we would expect since we would want the beta tensors to extract the same anatomical information from each image, regardless of the contrast. So how do we do this in terms of harmonization? Well, for harmonization, we need two different images. We need a source image, in this case from the IACL dataset, and a target image, in this case from the Site A dataset. We feed these into the encoder and produce our two latent spaces. We can see here that we have a theta and a beta for each of our source and target images. But for this process, we won't need the theta from the source image or the beta from the target image. We will just require the theta from the target image, which again, remember, it represents our contrast, and a beta from a source image, which represents our anatomy. This can be fed into the decoder to produce the harmonized image, which we can see represents the anatomy of the source image while having the contrast features of the target image. This is the intended result of harmonization. So how do we do this in a larger scale? Well, for this we pass all of our images from all three sites through our encoder. We calculate a mean theta value for images from our target site, specifically Site A. We can then use our individual beta values and that constant mean theta value to produce a harmonized version of each image. I'll show you again the original images and then their harmonized components after we've used that constant theta value. And we can see that these images are substantially more similar in terms of their contrast, while maintaining their anatomy and features of the actual brain. We can do a limited quantitative comparison between Site A and Site B because we have a couple of overlapping subjects, but remember, these are very difficult to acquire. We can see that the PSNR has increased between the original images at 26.1 and the harmonized images at 29.2. So in conclusion, we've directly trained a harmonization network without traveling subjects or GAN models. We've generated an interpretable latent space that allows synthesis of a spectrum of imaging contrasts, and we've shown that harmonization is possible by injecting a constant theta value. For a future direction, we'd like to use theta as a measure of contrast similarity, so that if we have an image analysis technique that's trained on a set of images, we can calculate the distribution of thetas for those images and find out if a new data set is within or outside of that distribution to tell us if we might need to use harmonization before we can specifically use that image analysis technique. I would like to thank all of the co-authors, specifically Leon Reid Zhu, who had a substantial contribution to this paper, as well as our other IACL team members, the fellows and coordinators at our neurology department, and all of our grant support. If you have any questions, my email address is at the bottom of this slide, and if you would like more information, you can scan this QR code for access to this video, our paper, and our graphical abstract. Thank you so much.